Okay, hi. In this podcast, we're going to consider the shapes and properties of some relatively simple covalent molecules that you would have encountered in your chemistry so far. We're going to look at some structure and bonding aspects that maybe you haven't looked at in such depth before, but that's the point of the podcast, is to just take you to a different level. Okay, we're going to consider the hydrides of carbon, nitrogen, oxygen, and fluorine. And the first molecule we're going to look at is methane, CH4. Now, CH4, as you would know it, you would normally write the formulae like this, and if you were to expand it into a Lewis type structure, which includes the covalent bonds, and also superimpose a dot and cross picture on the molecule to show that the valency electrons from carbon are coming from the 2s2 and 2p 2p shells, where the 1s2 shell is buried. These valency electrons, 4 of which are available to carbon, are paired up with electrons from hydrogen to form the hydride of carbon known as methane. And here we are putting the circles on that you may have used in the past for dot and cross pictures as well, just to bring a bit of familiarity to what we're talking about. Let's consider the shape of the molecule. Okay, methane, most textbooks will tell you, is tetrahedral. We're putting a different representation here, showing a wedge and a dash to give perspective to the molecule. The carbon sits at the middle of a tetrahedral arrangement of atoms, and if we connect up the hydrogens, you will see the tetrahedron appearing. So this molecule is tetrahedral. That means it's got 4 covalent bonds with bonding pairs of electrons in. If I superimpose a dot and cross pictures here as well, just to remind you. And these bonding pairs are going to repel one another around that central carbon, and the consequence is that the bond angle for the HCH angle is 109 degrees, and that's the angle that's quoted in textbooks as the tetrahedral angle. Okay, so that's methane out of the way. Let's consider the hydride of nitrogen, and you would normally hopefully write it with a line representation like this. You'd consider the electrons available to the nitrogen. Again, it's got 1s2s which are buried as an inner valency shell. Its outer valency shell is comprised of the 2s2 electrons and the 2p3 electrons, and that means that there are 5 electrons to consider around nitrogen, and other electrons, the other 3 electrons to complete nitrogen's octet, to complete its valency shell, are going to be supplied by hydrogen. And note that when hydrogen shares this electron, it also completes its valency shell and completes it to a 2. So remember the 2-8-8 rule that you would have learnt previously. Okay, let's reiterate the structure of methane, and then I'm going to show you a little trick that I've developed over the years to try and show people that they actually know a little more than they think when they learn the structure of methane. If you take the central carbon out of the structure of methane and rub hydrogen off, look what you are developing here. You are actually reconstructing the elements for ammonia, and superimpose a dot and cross picture around it, just like this. Now we've got a lone pair instead of 4 bonding pairs, a lone pair and 3 bonding pairs here, and the lone pair repels bonding pairs differently to a bonding pair. And in fact, I've just written the wrong angle here. Let me amend that, because the bond angle around the HNH arrangement is actually 107, not 105. That's a little bit small. And note we've gone down a couple of degrees from 109. So the bond angle HNH is compressed. And that's ammonia's structure. Now we're going to consider water. And hopefully you can see the approach that I'm taking now, and that is to build up on familiarity, things that you know about drawing structures, things that you need to be able to depict when you're discussing these matters. So here, let's have a look at oxygen's electron configuration. 1s2, 2s2, 2p4. It's further along the row. It's now got 6 outer valency electrons, and it needs another 2 to complete its octet. It gets those from hydrogen, and that's why we get the hydride of oxygen known as H2O, or obviously water. Let's do the same trick with methane again. Let's get rid of the atoms that we don't want from the methane structure. Let's change the central atom to be oxygen. And by doing this trick, it also gives you a sense that the molecular shape is maintained. So here we've got a tetrahedral arrangement of electron pairs, but often the molecule is not referred to as tetrahedral, although personally I like to think of it like that. It's actually referred to as an angular molecule quite commonly, particularly at A level. And that angle is 104, and again the reasons there are 2 lone pairs repelling 2 bonding pairs. Now here's an interesting comparison with H2S, which is a row below oxygen in the periodic table. The angle, the HSH angle, is 90 degrees, and that's incredibly small, and that's due to the large pairs of electrons that are in the non-bonding pairs. Okay, let's have a look at the final hydride, and that's the hydride of fluorine. It's also known as hydrogen fluoride. It's the molecule that makes hydrofluoric acid in aqueous conditions. So, electrons available to fluorine: 2s2, 2p5 in its outer valency shell. It's going to require an extra electron to complete its octet, and that's going to come from hydrogen in a covalent bonding situation. Now, we're going to take a departure at this point and start thinking about the electronegativity of the elements of the various things that we've been discussing. Now, electronegativity of fluorine is so much greater than hydrogen that the fluorine will attract more than its fair share of that covalency, and as a result the molecule is dipolar. We're going to use this idea of electronegativity and polarity in the molecule to look at the consequences for that, particularly in water. And what we are discussing for water also applies to ammonia, H2S. So here we are. Let's have a look at HF. When HF goes into water, it will fully dissociate. The hydrogen will leave the fluorine atom to complete its octet as a fluoride ion, and particularly if the water that interaction would happen if one molecule of HF met one molecule of H2O. Generally, if we pass HF gas into water, the solvent molecule is in excess. and that dissociation will occur, and also solvation of the resultant H3O plus ion and F minus ion occurs, and that confers stability on that equilibrium. One thing you might not have considered is the nature of H3O plus, something that you may have discussed. It's known as it can be known as the hydronium ion or the hydroxonium ion. You'll see it in textbooks differently. And look at it, it's got a very similar configuration to the NH3 molecule. Okay, let's move on a little bit. So that's what happens to HF in water. Now, what happens to water in water? Well, actually, we're not going to go into the ionization of water, self-ionization of water, but I am going to look a little more at what happens intermolecularly between two or more molecules of water. So let's consider one molecule of water with its dipolar bond. Now, what's happening here is that there's at least an electrostatic interaction between the hydrogen of one molecule, the molecule on the right, with that on the left, and that forms with the oxygen in the molecule on the left, and that forms a hydrogen bond. Now, these hydrogen bonds are partially electrostatic because of this attraction of a slightly positive charge with a slightly negative charge, due to the electronegativity difference between oxygen and hydrogen in the two molecules. But actually, more than that, a hydrogen bond has partial covalency. We won't go into the full details of that because it's not necessary, but that partial covalency does lead to a directional characteristic within hydrogen bonding, and bulk water will exist in the liquid phase, and it has an extended network of hydrogen bonds, and this network of hydrogen bonds is the thing that makes water a liquid at room temperature versus, say, H2S, which is an interesting comparison, as H2S is actually a gas at room temperature. You might want to think why that might be the case. If you think about the solid phase of water, ice, and particularly snowflakes, now you all probably have seen pictures of snowflakes and seen how pretty they are. They are highly symmetrical structures with repetitive patterns, and this sort of goes to confirm directional repetitive nature of the hydrogen bonding network. So we can use that as a bit of evidence.